Say. Hi, good afternoon, everyone. Thank you so much for joining us for our second webinar in our series of Advanced Geophysics Technology series. I'm Nadia Duplessis. I'm a geoenvironmental consultant from USK. And today's session is titled Magnetic Resonance Technologies for High-Resolution Hydrogeological Site Characterization. So just a few quick household notes. We really want to try and cap it to an hour. And Dr. Walsh is also happy to take questions during the session. And if time allows, we'll get a few questions in at the end. So please feel free to submit your questions in the chat throughout the presentation. So let me just quickly move on to Dr. Dave Walsh, and it is my great pleasure to introduce him, the founder and president of Vista Clara Incorporated. And over the past 22 years, he has led the development of NMR geophysical instrumentation for groundwater and subsurface investigations, including surface NMR systems and borehole logging technologies. We're very pleased and honored to have him with us today, and I think we're all looking forward to a very informative discussion. Thank you so much. Dr. Walsh, I'll hand over to you.
All right, thank you very much, everybody. I'm going to share my screen now. And as Nadia indicated, please just add questions as we go. I think the first part of the presentation is really important to understand. So if you have questions over the first 4 or 5 slides, please just ask. And because if you've got a question about it, there's probably other people who have the same question. All right, so my company, Vista Clara Inc., we're a US-based company. We also have a subsidiary in Canada now. Just a few of the people here, contacts myself, I'm the president, Daria is our chief scientist, and Warren manages our rentals and services. Magnetic resonance. So with magnetic resonance, what we're doing is we're basically detecting water directly. And what we're detecting is actually the hydrogen atom. So the hydrogen atom actually has a small magnetic moment. Most atoms do not. Like, for example, this H2O molecule, the oxygen does not have a magnetic moment. So the hydrogen has a magnetic moment because it has a single charged particle and it's spinning. So it kind of acts like a current loop. So this is what we're detecting when we use a magnetic resonance measurement. We're detecting the magnetic moment of those 2 hydrogens on that water molecule. So this measurement was discovered in the 1940s, and it has been used widely in organic chemistry ever since, using instrumentation such as this, and for the purpose of understanding the structure of organic molecules. Magnetic resonance is also the basis of medical MRI. So if you've ever gone and had a medical MRI exam, like I have, you basically go inside this big donut-shaped contraption, and that contraption performs magnetic resonance measurements on you for the purpose of generating high-resolution images of tissues and fluids in your body for the purpose of diagnosing injuries or disease, or hopefully the absence thereof. So what we're doing is we're using the same physics as these other 2 more well understood measurements. We're using magnetic resonance, same physics, but we're using it with a different type of instrumentation. It's a type of tool that goes down a hole in the ground, and we're using it for a different purpose, and that is to detect and measure the abundance of water that's in the ground, and also try to get more information on hydrogeologic properties, like is the water in a permeable formation or is it in clay, that sort of thing. So one note that's a common misconception is the confusion about the word nuclear. So nuclear magnetic resonance is basically the chemical term originally, And so this has nothing to do with the radioactive particles, emissions, or detection thereof. It simply refers to we're detecting the magnetic moment of the nucleus of the hydrogen. And so there's no radioactivity involved. We're just using a combination of magnetic fields, applied magnetic fields, to detect a weak magnetic field back from the hydrogen. Okay, so this is a key slide here. Please ask these couple slides here. So how does magnetic resonance relate to hydrogeology? Okay, so basically, remember, we're detecting the hydrogen atoms here. We're detecting basically a bulk magnetic moment that is from the large collection of these hydrogen atoms. So we're detecting water that's in the pore spaces here. This is kind of a little microscopic view of fine sediments here. And so we're not sensitive. NMR is not going to give you a signal from any of the rock or the grains, only from the water or any other fluids that are present. Okay, so your NMR signal that you detect is typically a weak alternating magnetic field that's generated from the water itself. And that's typically generated as or detected as a voltage on a detection coil. And so that voltage or that magnetic field has a form such as this. It has an initial amplitude. It is rotating at a particular frequency, and it is decaying over time. So the initial amplitude of that signal is simply directly proportional to the amount of water that you have in your sensitive zone of your instrument. So basically, if you have no water, that amplitude is 0. If you have twice as much water, you get twice as much signal. So it's basically a direct and linear measurement of volumetric water content. So that's a really nice thing to be able to directly measure water content non-invasively in situ. Okay, so that's a lot of people are be very happy with just that piece of information. But then there's the second property here, and that's the decay time. So the signal that's generated from the water in these pore spaces, it doesn't go on forever. It decays over time. And so the thing that normally governs that decay time is the pore size. So water in large pores, such as this one, will exhibit a long decay time. And water in smaller pores will exhibit a proportionally faster decay time. So just by looking at the amplitudes of your signal, you can tell how much water is, and by analyzing the decay times, you can tell whether the water is in large, medium, or small pores, or any distribution thereof. So based on those direct measurements, NMR can provide directly water content, volumetric water content, bulk porosity. That is, if the formation is completely saturated, then you're actually measuring porosity, which is the same as water content. And you also get a relative pore size distribution from your time decay spectrum. So these are all directly measured properties. And the relative pore size distribution, it really reflects basically the sediment type. So it's really most useful for just classification of sediments or rock. And estimated additional properties that you can estimate are the effective porosity. That is, some of the porosity may be drainable and some of it might not be, like water that's held closely in by capillary forces, surface tension, that will not typically drain under gravity, and water that's bound to clay. So you can segment the different fractions of water into mobile, capillary bound, and clay bound fractions based upon the relaxation times. Finally, you can also estimate hydraulic conductivity from all of these parameters using mathematical equations that relate those magnetic resonance measurements, the porosity, the time decays, etc., to hydraulic conductivity. I should say that these are just estimates over here. These are direct measurements on the left. Any questions about that before we get into instrumentation? We can always come back. All right, so basically three different categories of geophysical geophysical instrumentation and applications of magnetic resonance. Borehole logging, so direct push and CPT, in situ measurements, and surface NMR. So we'll go through all three, and after each introduction, I'm also going to give examples in different applications. So we'll start with borehole NMR logging. So this is the most widely used form of magnetic resonance in geophysics. And basically how it works is you've got this geophysical logging tool that goes down a well. In this case, you're going through a PVC casing. It also work with an open borehole. And it has permanent magnets inside the tool, and it also has induction coils. So the permanent magnets inside the tool cause a strong polarization of the water molecules. So you get basically a bigger signal than you would otherwise. Basically polarizes the hydrogen molecules, just kind of like the way a compass needle points towards the North Pole. Same concept. Okay, so this, and then the induction coils generate alternating fields that cause a coherent signal, basically a coherent rotation of that magnetization of the water. And you use the same detection coils to detect the weak magnetic field that's generated from the water. So in any case, this particular measurement, it's you can use it in PVC cased boreholes. You can use it in open boreholes, mud filled, air filled, water filled. That doesn't matter. The only thing you can't use it in is inside a metal casing. And that's because you're generating low radio frequency magnetic fields, and those fields will not penetrate metal. So there's a wide range of borehole sizes and a wide range of well construction. You know, you've got in the environmental remediation business in North America anyway, you've got millions and millions of 2-inch PVC cased wells. And you also have very large diameter wells that are used for groundwater production. So the key thing when you're going to use, the most important thing when you're going to use an NMR logging tool in a well is to understand the well construction and select a tool that is going to ensure that it's measuring out in the native formation and not inside the annular space. So the way these tools work, so for that reason, we have a wide range of borehole logging tools because they have different diameters of investigation. So the way the tools that our company makes anyway, the way that they work is you basically are only sensitive to water in a very thin cylindrical sensitive zone that are kind of shown here. So that in this figure, the borehole, the NMR logging tool is this yellow tool here. And in this case, we've got 3 different sensitive zones. So this tool can actually operate at 3 different diameters of investigation. But the key thing is each of these investigation zones, it's actually only a few millimeters thick. So you have a very specific zone in which the NMR measurement is happening. It's outside, ideally it's outside of the well, outside of the filter pack or the grout, and in an undisturbed formation. So that's the key thing when you're thinking about applying NMRs, to understand the well construction, including how much sort of roughness, rugosity you have. I guess one more thing is that you when you collect NMR data, basically you can see the final product as the log is happening. Basically, you can do the processing is mostly automated, and you can sort of develop that visual of all of your key parameters as the measurement is in progress. So this is just kind of an example here of how NMR data are reduced and analyzed. So this is an example from Utah in the United States. In this case, this is a log of a production well in a sandstone and shale hard rock situation. And so on the left here is the raw NMR data that's measured. Basically, these are the time decay that's measured directly. And so if you recall, so in this case, you've got function as a function of depth and also a function of time. So all of your NMR signals are basically starting on the left and decaying over time towards the right. So if you recall, water that's in large pores have a long decay time, right? Remember that? That's a key thing. So we can just look at the raw data here and we can see where the large pore water is. It's here. See these long signals. So this is basically the amplitude of the signal decaying from left to right. Excuse me. So there's a few zones here that you can see longer signals, and those are where you've got more permeable rock formation. So the next step is to do your time decay distribution, and you can look at this as a relative pore size distribution, basically. Very small pores are on the left, water in medium-sized pores in the middle, water in very large pores are over on the right. So again, just by inspection, you can kind of tell, okay, this is the very small pore water. That's actually water that's found in the small pores of shale. And down here, there's the most productive zone is obviously down here where you've got water in these larger pores, and that's sandstone. On the next step is to basically plot the total water content, the total porosity, and you can segment it into effective porosity, which is the dark blue, and capillary and clay-bound porosities. And finally, you can calculate estimates, quantitative estimates of hydraulic conductivity. So this is pretty good numbers down here for production, 10 to 100 meters per day. Okay, just some applications.
Sorry.
Yes.
Sorry, Dave, before we go on,
Yes.
we have a question about how far into the formation does an NMR logging tool investigate?
Perfect. Excellent. Thank you. So it depends on the size of the tool, basically. Smaller diameter tools do not see as far out. So you can basically control to some extent how far out the tool is seeing compared to its diameter. I don't want to get into the details of how that works, but basically you just tune it to different frequencies and you're basically selecting different diameters of investigation. But, well, for example, we have a small diameter tool over here on the left that's a 1 3/4 inch diameter tool. It's really designed for 2-inch PVC monitoring wells. So it will fit within that 2-inch PVC, and it sees out at diameters of 9 and 10 inches. So I'm not too familiar with the standards in Africa, but in North America, it's very common that you have a monitoring well that has basically a 2 to 3 inch annular space around the PVC. So typically you're drilling with 6.5 to 8 inch diameter drilling equipment. So your tool has to see out past that drilling disturbance, right? Now, on the other end of the scale, we got a 5 1/4 inch diameter tool that sees out and at 3 diameters of investigation between 16 and 21 inches. So that tool is particularly useful for logging large open pilot holes anywhere from 14 to 17 inches, which are also pretty common in the southwestern United States. So there's a range of logging tools. And the more is possible. You could make bigger tools that see out way farther, but that's kind of the general idea is to use the tool that's best for your type of well. Hope that answered the question.
Sorry, guys, I have a work from home situation in the background, but I think this also relates to the next question from Quentin about if it works through PVC casings, steel casing, and gravel pack, which is quite commonly used in South Africa.
Mm-hmm.
And then there's also a comment by Chris about the volumetric average, if you want to have a look at that.
Sure. Yes. So first of all, NMR logging will work through PVC, through fiberglass, through any type of plastic or non-conductive casing. and it will not work through a metal casing. It won't work through stainless steel, won't work through steel. So that's just a limitation. It just won't work through it. So the volumetric averaging is basically you have these sensitive zones and you're basically measuring whatever is in that sensitive zone, the water, the absence of water. And again, the size and the vertical length of that and the diameter depend on the logging tool. We have some tools that have a very some direct push tools that have a very high resolution vertically. Most of the borehole logging tools that we operate are anywhere from 4 to 15 inches, that vertical zone. So that basically, you're basically getting whatever's within that is contributing to your NMR signal. Hope that helped. Hope that answered that question. All right. This is an example of NMR logging for site characterization in environmental remediation. This is a very highly contaminated large remediation site near Las Vegas, Nevada. And they've been working at this site since the 1990s. But in this case, in environmental remediation, the vast majority of the time, NMR logging is used. It's to get high resolution hydrogeologic information to improve the conceptual site model. And it's basically the only tool that you can actually use in an existing PVC cased monitoring well to give you such information. You can't. So, I mean, if you've got the big value here is, typically in an environmental remediation investigation, you've already got a lot of PVC cased wells, or they're going to have a lot of PVC cased monitoring wells. So you can take NMR into that site and use it in these existing assets, these PVC cased wells, to get high resolution hydrogeologic information. For example, in this particular application, a 2-inch PVC well on one area of the site, here's the NMR log. You can see that there's a water table here. You see very little water above that. And you have basically a dual porosity. This is basically a semi-consolidated formation of some sort. So you've got some water in small pores, some water in larger pores, and particularly you've got a particularly high permeability right there at about 20 meters. So that's important for understanding how contaminants are moving through this site. And at another location, we have a 4-inch PVC cased monitoring well. And for that, you use a different tool that's a larger diameter that's able to see out farther. And in this case, you can also see water held in the unsaturated zone below 10 meters. There's two different formations. One has a lot higher porosity than the other. And there's also, again, a particularly permeable zone that's revealed at about 47 meters here. So those are really important things to understand. And so you can get that information from existing PVC cased monitoring wells. But this is an example in geotechnical application. In this case, the user was Fugro. They're a large geotechnical consulting firm. And they were doing a survey across the Thames River in London for basically siting a new tunnel under the Thames River. And so they were looking in this case, so basically they did a series of open borehole logs, including from a jackup drill platform over the river itself. And so they're drilling into the riverbed and they're trying to get information on where the permeable zones are, because they're going to need to know that to determine if, first of all, is it even feasible to do the tunnel in a certain location? And if it is, how do they plan for dewatering the ground while they're constructing the tunnel? So this is kind of an example. You got highly permeable materials to 15 meters, 15 to 25. It's more of a mix of finer grained materials. And even down here at the bottom, you have this very interesting chalk formation starting at about 40 meters. For groundwater resources, I don't know if you are familiar with this, but a lot of the world's lithium actually comes from groundwater. It's produced from from very highly saline brine in certain regions of the world, including this area in South America, in Chile. So NMR tools are used for optimizing basically well design and also even production over time. So this is an example at that site where you've got an NMR log of formations, of halite formations and other unconsolidated formations. And so the effective porosity here is shown in the blue, and the permeability basically are key to understanding what is the actual production capability. And you combine the effective porosity with the dissolved lithium content, and you basically, the mining company uses that to estimate the size of the resource. And so that's all important, and it's actually reported out in corporate, corporate reports for the investors. One more example in groundwater resources. This is from the southwestern United States, where NMR are used pretty regularly to optimize well design. And in this particular case, this is a new production well that's sited next to an old well that's not producing anymore. Basically, they have an old well that it's getting clogged up, a lot of sand coming in. So they need to replace it. And so they drilled a pilot well right next to it, like 50 feet away. And then the first thing they did with that, once they got that 16-inch well open hole, is to do the geophysical logs, including the NMR. And so this is the NMR log from that well. And you see there's a mix of coarse materials throughout here, coarse and fine materials. Most of the coarse materials look like they're at the bottom. You can see this here. This is where you got your longer time decays associated with water in larger pores. Your hydraulic conductivities are higher here, and your transmissivity. So all of these things indicate that you're going to get most of your production from this zone. So they actually did use this information to, the next step is to do some zone sampling. So basically then they create temporary wells in this borehole, and they do pumping tests to get water quality and hydraulic conductivity measurements directly in certain zones. So the NMR is used to basically pick those zones for sampling. And this particular company, they specialize in taking this NMR data and predicting what the well yield is going to be just from the NMR data alone. And so they estimated before actually constructing the well that they'd get between 2,000 and 3,500 gallons per minute from this well. And they ended up screening it down here. And the actual, after the $2 or $3 million were spent to install this well, they actually got 3,000 gallons a minute. So I'm not saying that this is, you're always going to get that accurate, but these guys do get pretty close. They're reporting to us that they typically get within 50%, just using the NMR log to predict what the well yield is going to be. Okay, so finally, last application in borehole logging. Yes, Nadia.
Just, I think, to go back to your previous discussion, we've got two separate questions about how you differentiate between the saturated zone and the water table, and then also about how salinity would affect your results.
Okay, great questions.
Also, if you maybe want to have a look at Chris's longer question, if at all, maybe you can summarize or you can bring it all together about how drilling fluids and mud might also introduce moisture into the system.
Fabulous. I love all three questions. Now I got to remember them. Okay, the first is the water table. So the NMR measurement it is basically showing water content here. Water content. So it does not actually detect a water table. You have to interpret a water table. So in this case, I can interpret the water table starts at 6 meters because there's basically no water, no water above here, very little. And then all of a sudden, we've got more water. okay? But it doesn't actually detect the water table. It's basically, it's detecting whatever water's there. And, you know, there's always some water in the unsaturated zone, especially in fine sediments. It tends to get held up. So the second question was, I forgot. What was the second question?
Second question was about, does water salinity affect the results?
Yes, actually, to a very large extent, no, because NMR is basically sensitive just to the water itself and to the pore size, the environment that it's in. So the salinity of the water or the electrical properties of the water largely do not have an effect on the NMR data. Now, if we were operating at a very high frequency or trying to see out very far through very saline water, there would be some attenuation of the NMR signal just because of the skin effect of you know, very conductive water. But and it also does affect a highly saline environment around the tool. Also does affect the performance of the coil itself. The detection coil actually gets loaded by that, so it changes. But we can track that effect and compensate for that. So to a large extent, really, in a situation like this where you have very highly saline groundwater, it doesn't affect it. It doesn't affect it even in these very highly saline environments like you have in lithium brine, which is more saline than seawater, a lot more. And then the last question, could you again remind me what the last question? Oh, drilling mud.
It was,
yes,
yeah, it was volumetric averages, and does it compromise the data, like drilling fluids and mud and other introduced moisture?
Drilling fluids can affect your measurement. I don't have a good picture of it here, but so if you've got coarse materials, coarse materials in the formation itself, and you have drilling fluid, that drilling fluid will tend to migrate into those, right? You know, you have very permeable, large pore spaces, drilling fluid will go some ways into the formation. And sometimes drilling fluid can have a very fast relaxation time. So normally we just assume that we have water and that has a very long relaxation time, very, very long decay time. But if you have drilling mud, sometimes it itself can have a fast relaxation time and you're still going to detect it. So if you've got like drilling fluid with a fast relaxation time that's in large pores, you're going to get a big signal from it, but it's going to have a fast relaxation time. And so you would misinterpret it potentially as being bound water, right? Because clay bound water also have a fast relaxation time. So you do have to be careful when you're doing an open hole log with drilling fluid, or even logging, you know, in a well that was at any point drilled with drilling fluid. And it helps to have multiple zones of investigation like you see here, because then if you see a difference between the inner shell and the outer, then you can say, okay, well, I'm going to only trust the outer because, and typically what you'll see is like faster relaxing signals in here versus out there. And so this is sort of a quality control tool that you can use. And sometimes you have big washouts and lots of drilling fluid, and it just takes a trained interpreter to just say, well, it looks like we've got some drilling mud invasion. It does happen, and that's a great question. Okay. Finally,
oh, sorry.
one more.
You want to address another question, or do you want to move on?
Well, we've only got 20 minutes. I think I better speed up here.
Okay, no, cool.
Maybe,
and then
maybe we'll get that.
Okay, then we'll
question.
Address questions at the end. Yeah?
Yes.
Awesome.
And I can stay late. Anybody wants to stay late. Okay,
Thank
so
you.
finally, magnetic resonance is also can be sensitive to any changes that are happening in the pore space, any physical changes, particularly like development of biofouling in the pore space. That's because it's sensitive to what happens in the pore space, what's physically happening in there. So this is one example of we're using NMR to monitor a remediation process in the formation using NMR. In this case, there's a particular remediation that involves injecting certain chemicals into the groundwater to remove dissolved phase uranium from the water and depositing that as a precipitate in the pore space itself. And so this is an example where we're monitoring over time in these down gradient monitoring wells. Basically, what you see is this is basically your as NMR estimated hydraulic conductivity. As the precipitation is happening in the pore spaces, as a result of that remediation reaction, you see a big drop in the hydraulic conductivity in these two zones here. So this is applicable to precipitation. I think it's applicable to CO2 injection, biofouling, and probably a lot of other types of remediation or other activity. All right, I'm going to go forward to direct push and CPT. So this is a different type of instrumentation. Basically, concept is the same. You've got a borehole logging tool. These are very small, though. They operate from a small battery-operated toolbox size thing and a laptop and a cable. And they're also able to be deployed by direct push or CPT machine. Basically, the concept of the measurement is the same. The interpretation is the same. It's just a different form of instrumentation that's smaller scale, designed for smaller scale in situ stuff. So the way the direct push measurement works is first you push down empty drill rods until you get to your maximum depth. Then you deploy the tool down to the bottom of that, hold the tool in place with these thin push rods, use the machine to retract the drill rods out. That pushes the point out, the drill point, which is left in the ground, and that exposes the NMR sensor to the formation, and you do your NMR measurements as you're going up. So I won't go through that. This is an example. I think one of the key things about this is you don't have those drilling effects. You know, you don't have washouts, you don't have drilling mud, you don't have to worry about any of that. You're really getting a very, very precise in situ measurement with minimal disturbance. And you can get very high resolution results such as this. In this case, this is the tool there after doing a direct push log. These are mostly fine silts here, a little bit of organic material there. Again, this is the classification capability of NMR. And there's a very kind of sharp transition at this site to a very well-sorted sand and gravel deposit. And then it's back to some more silty stuff and kind of an interbedded mix of sands and silts down here. This is another example. This is in Kansas. Here you've got basically sands and gravels, alluvial deposits from the surface to 10 meters, and then a sharp transition to a clay, a very dense clay in this case. So you can clearly see the water table there, where very little water above the saturated zone. And one thing I want to point out is right there, that is a particularly coarse gravel. And so you can use NMR to differentiate, okay, there's medium sand, there's gravel, there's some finer sands through here. And estimating hydraulic conductivity, in this case, it's up to about 1,000 meters a day. Well, it's gravel. And compared to an HPT, which is a much more widely used tool, that tool can only measure or estimate hydraulic conductivity up to about 30 meters per day. It can't differentiate larger than that simply because it can't get enough flow and enough pressure to do a hydraulic measurement. I also want to point out down here in this clay formation, this is very dense, but there's actually a couple spots in that clay where it's actually more of a silt-like material. So this sort of information, this sort of precision you can get with a direct push NMR measurement. You can also deploy direct push from CPT rigs. Basically, works exactly the same way. You just have a kind of a different looking drilling vehicle there. And this particular example is in mine tailings, and mine tailings are you know, a pretty good developing market for NMR because the water content is really critical for assessing liquefaction potential in these dams. There's been a lot of really high profile failures, including some disastrous ones that killed over 200 people in Brazil. So understanding what the void ratio is, basically the different depositions of different sizes of particles and how much water is held at any particular time. Those are all very, very useful for assessing stability of mine tailings. Finally, you can use a tool like this even in just a really simple little backyard way here. In this case, we've just got like a PVC contraption here. There's basically a 1.5-inch PVC tube. We just put a plastic auger on the bottom of it, and you can just screw this thing into the ground, and now you've got like a temporary well that you can use with your NMR tool to do high resolution measurements. In this case, we've got a water table very close to the surface, and what you see here, these are also fine sediments, a lot of organics, a lot of organic material. Look at that, it's 80% porosity. And you're kind of seeing the capillary fringe here from the surface down to where it's fully saturated. All right, this is a new technology. This is a combination of CPT and NMR tool. So it's just, I have, people, geotechnical engineers maybe on the call here. Basically, CPT is a cone penetrometer. It's very widely used in geotechnical investigations. And so this tool has a CPT cone on the bottom, which measures basically the resistance of the ground to this tool being pushed in. And it also has an NMR sensor just above it. So basically, this tool does geomechanical measurements and NMR measurements in a single push. And I'm running a little short of time, so I'll speed through this. But here's an example on land. Basically, your CPT data over here. This is basically your tip resistance, and this is an example from Kansas. We have an unsaturated zone here, mostly fine sediments, a lot of water held in those fine sediments. And then below the water table, you've got basically the water's filling all the pore spaces. So you've got mostly fine sediments. You've got a pretty well sorted sand and gravel aquifer down here. It grades from a little bit finer to a little bit coarser as you go down. And so you have these you got these geomechanical and hydrogeologic information that are perfectly correlated with each other and useful for a lot of investigations. This is an example using this tool over lake bed sediments. In this case, it's very soft lake bed sediments. Not much to say here. Both of the measurements are correlate, pick out where there's a little bit of sand mixed in there. See the tip resistance goes up, a little bit more mobile water content, a little bit longer relaxation times. And this has also been used offshore. This is one of the primary markets for this tool is for offshore geotechnical investigations, particularly for offshore wind. In this case, the tool is actually deployed from an undersea drilling rig that is lowered to the seabed, and then it's pushed in from there. And so this is an example of NMR data and CPT data from the seabed. In this case, you've got some fine sediments here, silty sediments, and then a layer of deposit of sand here, and then a mix below that. All right, now I'm back on schedule. Finally, surface NMR. This is totally different from the other stuff I've talked about so far. So this is still magnetic resonance, but it's a lot different. It's completely non-invasive. So the way this works is we use the Earth's magnetic field to polarize the water, basically. So as you're sitting there watching this presentation, all of the water in your body actually has a small magnetic moment, and it's polarized in the direction of the Earth's magnetic field, wherever you are. Okay, so that's the concept, is we we already have some magnetization because the Earth is polarizing the water for us. And the way this measurement works is we set a big loop on the surface of the Earth. And we send these big current pulses through that, and that activates a coherent precessing signal from that weak magnetization of the water. And then we use that same loop to detect the water, the signal from the water. So the key values of this is totally non-invasive, completely non-invasive. There's no drilling required. You don't even have to make contact with the surface of the Earth. It directly detects water. It images it to some resolution. So now it does have limitations. The main limitations are it's very sensitive to noise because that big loop is also very sensitive to any electromagnetic fields that are generated from nearby power lines, etc. It also doesn't detect most of the water in very fine materials. It's really good at detecting water in large pores, and that just has to do with the physics of the equipment that's used. And finally, water that's in sediments with high magnetic susceptibility, or even like underlying geology that causes gradients in the Earth's magnetic field, can really complicate detection. So these are significant limitations, but given that, when it's applicable, in situations where it's applicable, it's really cool because you're detecting water and you're imaging it directly. So I think the best thing to do is kind of skip ahead to a few examples and then take some questions at the end. Here's a couple of examples in the same area near Crested Butte, Colorado. One study area is down here by this river in the river valley, and then there's another measurement area way up in this basin, alpine basin. And so down in the river area, the objective was to understand what's the aquifer. Are there aquifers here? What do they look like? So this is a surface NMR measurement done with a single loop here. This took a total of 2 hours to lay the loops out, do the measurement, and pick things up. So in 2 hours, we got this picture here that showed us basically the distribution of water and in different pore sizes versus depth. And so this actually revealed an aquifer that was not previously known. So everybody, hydrologists around here assumed, yeah, there's going to be a superficial aquifer and then we're going to hit bedrock. No, there's actually a second aquifer there. And they ended up drilling there and confirmed it. Up in the high alpine bowl, in this case, there's a lot of heavy metals that are drained out of this valley, and some of it's probably naturally occurring. Some of it's probably from old abandoned mines that they fill up with water and then they drain through and bring heavy metals. So those heavy metals get back down into the river there, and it's a problem. So the question here is to understand, okay, how is water moving through the ground up here in this alpine bowl? So laying out a single surface loop here, we can see that we've got a lot of water just below the surface in permeable materials. And then there's an low permeability layer here that has a lot of water in it as well. And then there's some very low porosity, but large pore water down below. So I interpret this as, okay, these are unconsolidated materials here. Most of the water is moving through them. This is a high porosity shale, and this is fractures in a low porosity shale underlying the whole system. And finally, you can use surface NMR in a two-dimensional mode just by simply moving your loop along a line and taking successive measurements. So in this case, the question was, way up in this alpine bowl, was there water moving right underneath this rock slide? And if so, where? So we did a series of measurements, 19 measurements in all across basically this line. This was done in basically about 4 hours, just moving a small 10-meter loop across. And this is the result. So you can see that we detected water in the very near surface in the top few meters. but it was mostly just in this area here. There wasn't any significant water detected over on this side of the line, and there was a little bit less there. So most of the water is moving through here, and it's very shallow. So that's my presentation. Now I'm happy to take any questions. I think really, in summary, I think the really cool thing about magnetic resonance is that you are detecting water directly but non-invasively through an application of magnetic fields. And I think it's just a very rich signal environment that you're working with. And that's why medical MRI is so valuable in medicine, is because it's such a powerful measurement. It's sensitive to these things that are very a lot of different things that are very interesting. So that's why we like it. That's why we do it. So thank you
Awesome.
very much.
Thank
And
you
I'm
so
happy
much,
to.
Dave. That was really, really great. Like, it took me back to my student days suddenly, and I feel like I've got a lot of background research to do. You've ignited some questions, and I can see that our chat is blowing up. So there's a lot of questions and a lot of people that would like to talk to you.
Great.
I wonder if we can just sort of do the formal wrap up, and then those that would like Dave kindly offered to stay behind and have chats with everyone. That is because it is also only 6 a.m. for him, so he's got the whole day ahead to talk to to talk to everyone.
Yeah, I got all day. Yeah, sure. I will stay until anybody has a question that's unanswered.
Okay, awesome. Then I just quickly can you guys see my screen? I'm not sure.
No.
Oh, yeah.
Yes.
Okay, wonderful. I would just like to acknowledge our partners assisting us with this webinar series, GSSA Groundwater Division, and where are we now? All of these guys. And then a very important reminder of our upcoming webinars. Webinar 3, which would be next week, Advanced Geophysics Technologies, Stop Drilling Blind. That sounds like a good one, and it's presented by HTIS. And then the week after, we've got Transient Electromagnetics. So this will also be widely advertised as on LinkedIn and through all our partners. Thank you so much, Dave. This was, yeah, that's, as you can see from the chat section, all the questions. This you hit the spot here. Thank you so much. Much appreciated.
They've asked if they can get the recording. I suppose you can. Yeah.
Yeah, I'm sure we can make a plan. I
PowerPoint.
think
I can forward the PowerPoint to Steve and Nadia and distribute it. I'll just make a PDF out of it and forward it today.
awesome. Do you have access to the chat?
I can pull it up here. Yes, let's see.
There's quite a long list of
Okay,
questions that have
if
come in.
I'm trying to go back, sensitivity of the tools, measurements in the wells with collapses.
Yeah, I think we went up to 1534, the one about how does the data from primary aquifer compare with that of a fractured rock aquifer? And then it
Okay,
just went on. You're gonna
sure.
be here a
So
while.
primary intergranular aquifer. So yes, often you have both, right? Sandstone's going to have what I refer to as matrix porosity versus fracture porosity. So like a sandstone frequently has both. And you don't necessarily always know the difference by looking at the NMR signal, because you can have water in fractures that has like similar relaxation time to water that's in large pore spaces within a sandstone or limestone. Limestone also has some, just wild distributions of pore sizes, sometimes very, very small, sometimes huge, and fractures. So I guess every type of rock has a kind of unique NMR signature, it has its unique pore size distribution, and the NMR measurement will reflect that. Now, if you've got rocks with very low matrix porosity, like granite, then basically any water that you do detect is in fractures. So, and often it's very low. You can have a hard rock aquifer that can be very productive, but have extremely low porosity, because it might have a 1% effective porosity, and it's all just in the fractures. So, but the NMR in that case will detect that water and quantify it. It can be difficult because it's such a low amount, but tool operate at 3 frequencies, resulting in the 3 radius of investigations. I ask this because at the beginning you posted different tool diameters targeting different radius investigations. Yes, all of our NMR logging tools have either 2 or 3 frequencies. So they're working at 3 different radiuses of investigation. And so that gives you some ability to use each tool in a wider range of borehole sizes. But we also have each tool has its own, each type of tool, each tool diameter has its own set of diameters of investigation. So the bigger the tool, the bigger the diameters of investigation. So generally, to get good signal to noise ratio, effective logging speeds that are useful, we tend to kind of fall with having those diameters of investigation being between like 3 and 5 times the diameter of the tool. Okay, so if you've got a small diameter tool, you think like 3 to 5 times that diameter is where the zones are typically. Given that the NMR measures from a thin shell, to what extent can it underrepresent or overrepresent fractures? Good question. I guess you have to, when you're interpreting it, you're assuming that the fractures or the water content within the shell is distributed isotropically or uniformly, and that may not be the case. So you could, for example, you could have a cylindrical sensitive zone that's, let's say, 10 inches tall, and that so you're integrating basically all the water into fractures there. And so if you've got like let's call it this. So let's call it a 20 centimeter shell. And then you've got a 1 centimeter fracture going horizontally that has 100% water in that 1 centimeter. So then your NMR is going to measure a porosity of 5% over the entire shell. So within that fracture, the water content is actually, the porosity is 100%. And within the rest of the sensitive zone, it's 0%, right? So it does average over whatever's in that sensitive zone. How do you handle measurements in wells with collapses that affect the regularity of the walls? Should tool diameter be changed in the affected intervals? If you have the option or the luxury of changing to different tool sizes, you can always do that. It's really good to have a caliper log before you use the NMR tool, because then you can see if there's big washouts, and also you can see if there's like cave-ins and constrictions that you're going to get the tool stuck, perhaps. generally, yeah, if you've got a caliper log, you can load that, plot that alongside your NMR data, and anywhere that the caliper is getting close to or even exceeding the diameter of where the NMR measurement is, you can just see that and say, okay, we have to discount whatever the NMR is saying there because it's certainly getting drilling mud or water from the borehole. Next question, given the sensitivity of the tools, how do you calibrate or which measurements do you use to calibrate the results and remove the noise? So you calibrate the tool basically by putting it in 100% water. So basically you just put it in a tank of water and then it measures basically the sensitivity to a very known quantity of water content, which is 100%. And so that basically gives you your scaling between your detected voltage and water content. In terms of noise, NMR measurements always have random noise. So the NMR signal is very small. It's a difficult measurement to do because it's a very small signal that you're detecting. And so ideally, you're limited by the noise from the coil itself, just the resistive noise generated from the resistance in the coil, and also the input noise of the preamplifier. So even when you've got very low noise conditions, you're always going to have some random noise. And so the NMR signal is going to have the underlying decay plus some noise on it. And that noise basically generates a variance, a random variance in your estimated parameters, such as water content, hydraulic conductivity. To remove noise, the best thing you can do if you have excess noise is to average your data vertically or just sit there and average longer. In the case of surface NMR, you just sit there and keep signal averaging. And actually, there's a really powerful technique in surface NMR where we use additional detection coils and we move them towards the noise source, like move it towards a power line. And then in post-processing, we use that data, the noise data, to cancel the noise on the detection loop. And sometimes it's really, you can get 2 orders of magnitude of noise reduction. It actually makes surface NMR feasible in a lot of situations when it otherwise would not be. Next question, do you have examples from applying NMR igneous rocks? Given that igneous rocks have low porosity, what are the limitations? Well, that's it. Basically, I've discussed it before. You've got basically little to no matrix porosity, and you've got a small amount of water and fractures. And you've also got noise. You always got that noise. So it does get more challenging to use NMR in very low porosity because you just got a very small signal that you're trying to detect. However, yes, people use it. We've used it. The other thing about igneous rocks is sometimes they have a high magnetic susceptibility, and that can also interfere with detection. I'd say for magnetic susceptibility, for borehole logging tools, you generally start to see, you can expect to see maybe some underestimation of water when your magnetic susceptibility is between 10 to the -3 and 10 to the -2 SI units. So that's a moderately high magnetic susceptibility. And then above 10 to the -2, you can expect to see a very significant underestimation of water content. Using the outputs from NMR, is it possible to obtain or estimate soil and/or rock mechanics parameters, which is important for dam engineering? So you can estimate or you can calculate density, bulk density from NMR porosity alone. Basically, you just, as long as you've got an accurate estimate of the porosity from NMR, that's basically your void ratio. And so you can estimate the in situ bulk density with just by assuming that the rock dry density is 2.65 grams per centimeter cube. We've done that. We've done that and compared it with some of the offshore data compared to lab data, and it's very impressive. So I guess the other mechanics properties, you can, with sediments, you can definitely like tell the difference, clearly tell the difference between fine sediments and coarse sediments, just by looking at the relaxation times. Okay, next question. Do you produce 3D interpretations from multiple downhole measurements similar to the oil industry? I do not, but I can't think. I do know that in the remediation business, yes, I've seen consultants do that. They import their NMR logging data from multiple wells or multiple direct push measurements, and they have a 3D visualization of that data that's within their conceptual site model. So we don't usually get involved in that. You know, we basically design and develop and manufacture the technology, and other people use it. Next question, could you tell us a little bit more about the person deployed NMR for shallow in situ? Yes. So basically that system, it has a control unit. It's about the size of a toolbox. You pick it up with one hand. It's battery powered. And then you have a short cable that plugs into that, and then the other part plugs into the probe. And the probes are short. They're really easily portable, and they so a single person can walk around and do measurements in shallow boreholes, shallow PVC cased wells. So it's very convenient. You can hike into places with it. You can deploy it with direct push or CPT, other types of direct in situ drilling. The main limitations of it has very high signal to noise ratio. Main limitation is that it doesn't see out as far as the borehole logging tools. So those in situ tools, they have sensitive zones that are 5 and 6 inch diameter, which is fine if you just augured a 3-inch hole in the ground and you're just doing a measurement in that. Or if you've got like a geoprobe installed 2-inch PVC, it's great for that. But it won't be useful if you've got like a borehole that was drilled with 7-inch drilling, and then there was a 2-inch PVC in the middle, because then that dart tool is just going to be seeing in the annular space. It won't be seeing out. So that's how that tool works. It's very popular amongst researchers because you can do all sorts of interesting measurements with it. Laboratory measurements, you can do, investigations of permafrost, you can do investigations of all sorts of monitoring of changes in the formation due to a remediation process. So let's see. Next question, what would be the max depth of penetration for surface NMR, or does one need to use a much bigger loop at the expense of noise? Maximum, I'd say, is about 100 meters, and you need a big loop for that. So basically, your depth of investigation with surface NMR is about the same size as the diameter of the loop that you're using. And for all practical purposes, and most of the time, that limits out at about 100 meters. You try to go much bigger or deeper than that, and you actually start getting unable to get enough current into the coil to get any deeper anyway. So I tell people generally 100 meters. And if you have a lot of noise, you may have to switch to a figure-8 style loop to cancel some of that noise, and that also limits your depth of investigation for surface NMR. Next question, can you just do the upfront theory again? How it works and what is direct measurements and what is derived? Yes. Why don't I do that right now? I'll share this presentation and go back to that, because that is kind of, that's a pretty key. Okay, another one just came in with ice. That's a great question. So ice, you do not get an NMR signal from ice. Frozen water, we do not detect frozen water with this type of NMR, only liquid water. So that's what makes it really useful in permafrost investigation, because you can tell where the ground is frozen and where it's not. Okay, so the hydrogeologic properties. So again, the NMR signal is generated from the water itself. The water has a magnetic moment. each of these hydrogen atoms is like a little bar magnet. Think of it that way. Each hydrogen atom is a small bar magnet. And when we expose this water to a strong magnetic field, a static field, those bar magnets tend to point in the same direction, just like a bunch of compass needles would point to the North Pole, same concept. And so when you get all these little tiny magnetic moments, all these little bar magnets pointing in the same direction, then you get actually a magnetic field that is measurable because it's big enough that, hey, even though they're all tiny, there's enough of it that we can measure that magnetic field from the collection of them. And so the measurement is actually done by applying a second magnetic field that's alternating. And that causes these magnetic moment from the water to start spinning around in phase with each other. And so now you have a rotating magnetic moment that's circularly rotating around in space, and that creates its own magnetic field, and that's what we detect. So basically, if you have no water, then you don't have any signal. There's no source of signal. If you just have dry rock, you don't get any NMR signal. And if you have partial saturation, you've got some water, then you'll get a certain amount of signal. If you have twice as much water of that, you'll get twice as big of a signal. Okay, so that's what you're directly measuring, is that magnetization from the water itself. And so the initial amplitude of the signal you detect is directly and linearly proportional to the volumetric water content. So if the pore space is completely saturated, then the volumetric water content is the same as the porosity, is the same as the void ratio. So in that case, if it's fully saturated, you're measuring total porosity and you're measuring void ratio directly with NMR. And then the second thing you're measuring is how fast that signal is decaying over time. And the decay time is governed by the pore size that the water is in. And I'll give a quick explanation of how that works, because I think it's helpful to understand. So the water molecules in that pore space, even if you don't have any flow, they're still moving at random. There's Brownian motion. So all of the individual water molecules are kind of randomly moving around in those pore spaces. And so once you activate that NMR process and you get those magnetic moments spinning in phase, that will continue generally until one of the hydrogen atoms or the water molecule gets close to or bumps into a grain surface. So when it bumps into a grain surface, then it stops rotating coherently. It disturbs it, right? So over time, as water molecules randomly migrate to and bump into grain surfaces, that's what leads to the overall decay of the NMR signal. Okay, so water that's in a very large volume pore, it takes a long time for all those water molecules to randomly migrate over to a grain surface so that they'll basically get spoiled and no longer contribute. Whereas in a very small pore space, it doesn't take long at all for those water molecules to get near a grain surface and bump into it. So think of it this way. You can kind of think of it like if you, a person, are, let's say you're blindfolded and you're just walking around at random in a room. And so if you are in a really large room, like say a big, huge auditorium, and you're walking around at random blindly, it is going to take you quite some time before you finally find a wall, right? But if you're in a small closet and you're walking around randomly, you're going to hit something really quick. And so that's what's actually happening that relates this time decay to basically the pore size. So we're basically measuring how long it's taking water molecules to randomly go around in this pore space and find a surface that's going to cause it to basically stop spinning coherently. So the direct measurements are volumetric water content. And if if the medium is fully saturated, then you're also directly measuring the total porosity and the void ratio. And we're also getting direct measurement of the time decay spectrum. And it's, the time decay and its distribution, which is effectively a relative pore size distribution. The estimated properties are the segmentation of the total water content into different fractions being drainable and non-drainable, and also the estimates of hydraulic conductivity. These are the farthest from a direct measurement, hydraulic conductivity, because in this case, you're just estimating that through a mathematical model that relates hydraulic conductivity back to these, basically the total porosity and the time decay.
Oh goodness, I feel like we've lost you there, Dave. Oh no, it seems Dave is frozen or having some issues. So those of you that are still online and would still like to chat, you can contact us. I guess, yes, we will be able to receive a recording. I'm sure we can make that happen. So, oh yeah, we lost Dave completely now. So thank you so much, everyone. Please do email us with further questions and further engagement. Thanks so much for all the questions. It was really helpful. Cool. Then we'll see you guys next week for our next installment. It was great. Thank you.